Okay, Assalamualaikum warahmatullahi wabarakatuh. So we continue with week number 1, lecture number 3, part 2. So we see in lecture number 2, we see the stochastic quantity. So now we're going to see the non-stochastic quantities. Okay, when we do the counting. Okay, so for a given condition, its value can in principle be predicted by the calculation. Okay, so a point function defined for infinitesimal volume. So it is continuous and infinitesimal function of space and time, and one may speak it of its spatial gradient and time rate of change. Okay, so we can expect the the mean number of counting the particle that coming through that point P. Okay, so its value is equal to or based upon the expectation value of a related stochastic quantity. So if that one exists. Okay, so in general, it does not need to be related to stochastic quantities. Say they are related in this ionization radiation. Okay, so these are the non-stochastic quantities. We have 4. Okay, so the first one is the flux or fluence. Then the flux density or the fluence rate. The next is energy fluence, and then the energy flux density. Okay, so first we see the fluence. So a number of rays crossing an infinitesimal area surrounding point P defined as a flux or a fluence. Okay, meter per 1 meter to the power of -2. Okay, so P equal to D and E over D A, where the N is the expression value of the number of rays tracking a finite space surrounding point P from T0 to T, and dA is the circle of that point. Okay, so we have here all the ray. So this is only one ray, but if we have a lot of ray, so the ray passing through this circle area. Okay, so we have this flux or the fluence of the ray. Okay, so next is the flux density or the fluence rate or at P. Okay, so sebagai contoh macam uh, dekat tol, again dekat tol, kalau kita ambil aliran trafik dekat tol, okay, kadang-kadang ada kereta banyak, kadang-kadang ada kereta sikit. Okay, so we see these are the flux density of this radiation. Okay, so var phi equal to d p over dt, or d over dt, d and e over dA. So where dA is the increment of fluence during the infinitesimal time interval dt at time t, the unit is meter minus 2 as second minus 1. Okay, so we can see that these are the flux of the radiation coming from time to time. Okay, so if the flux, we want to find the flux between T0, so we start the stopwatch, then we stop the stopwatch, so T0 T1, so we can get the flux or the number of ray passing through that point at during that time. Okay, so next is the energy fluence. Okay, so as we know that the radiation, we have a lot of energy. Okay, depend on the radiation source, so it depend on we have a lot of different energy. Okay, so the energy fluence, if the energy that passing, or the flux of energy that passing through that point, so the sum of energy from all ray hitting the target. Okay, so this psi equal to dr over dA, so where r is this expression value of the total energy carried by all the NE. striking at a finite sphere surrounding point P from T0 to T1. And if we are using the mono energetic source, or let me say we only use one radiation source, for example the electron with a fixed energy, let's say 3.5 megaelectron volt. Okay, so the flux energy fluence or energy flux for that time interval will be psi equal to E times the P. Okay, psi equal to E times P. Okay, so we can calculate the energy deposited into that molecule or into that onto that point P. Okay. Okay, so these are energy flux density. So the at a certain time, so the speed. Okay, at any time t, the interval we may define the energy flux density or energy fluence rate at p. So psi equal to d psi over dt, d over t, dr over dA. So energy fluence from T0 to T1 can be calculated using integrate in this integration. And or if a constant energy flux, so meaning that let's say for each time, contoh lagi macam dekat toll, dalam setiap jam 10 kereta passing through the toll, so we can calculate the energy flux, this for example this energy flux density using psi times delta t. Okay, so we can get the number of for example this radiation passing through this point. Okay, so that is the non-stochastic quantities. But here when we do the experiment, or we use the experimental apparatus, okay, so we have the source and we have the detector, we have the target, the cell target. Okay, so the source, the radiation from the source usually is collimated, okay, ataupun tertumpu kepada satu arah. Okay, okay, so for that we can use this distribution. Okay, so here you can see that most radiation interaction are dependent upon the energy of the ray. Okay, the type of the ray radiation, and the sensitivity of radiation detector typically depend on the direction of incident of the ray striking it. Okay, so this one we are talking about the detector. Okay, macam mana apa radiation tu masuk ke dalam radiator detector. Okay, so kalau ada detector bulat, maknanya radiation yang datang dan masuk ke dalam dia punya cermin akan dikira. Di luar cermin tak akan dikira. Okay. Okay, so here we can see that these are z-axis, theta, beta, and the r. Okay, r. Okay, generally the flux density, fluence, energy flux density or energy fluence depend on all variable theta, beta, and E, energy. Okay, so here one could measure the flux density at any time t and at point P as a function of kinetic or quantum energy E and of the polar angle of incident theta or beta. Okay, so differential flux density, okay, dari mana dia masuk is equal to 1 phi theta, beta, and E, a function of beta, theta, beta, and E. Okay, so these are the unit. Meter squared. 2 power minus 2, S2 minus 1, radian minus 1, kiloelectron volt minus 1. Okay, so when we take the integration over all the flux density, so we can get the energy flux density. Okay, so maknanya ini dari mana dia masuk, daripada theta equal to 20, theta equal to 21, theta from 22, so we can get this the different energy or different response. Okay, so if frequency is function of energy only, okay, kalau kita cuma let's say the detector is sensitive for the energy only, so such division is called the energy spectrum, and integration over all angular variable give flux density spectrum of depend on the energy, and integration of this var pi dot E over all energy of the ray represent then give the flux density the flux. Okay, so this one we get E naught to E max var pi E d E. Okay, so for this certain energy, so what are the flux density for E1, E2, E3, E4, E5, E6, and all the spectrum. Okay, so here we can see that a flat distribution of photon the flux density for these are the example. Okay, so photon energy E gamma energy E max. So you can see that it is sensitive and it only taking the same number of energy. Okay, the same number of energy. Okay, so here you can see that. So energy flux density spectrum. So it's found by pi psi E equal to exponential var pi E exponential. Okay, so this one is the energy can be absorbed by the detector or the molecule. Okay, so here you can see. Okay, and if the detector depend on the angular distribution, so if the field is symmetrical with respect to the vertical z-axis, so here we can see that this z-axis, so these are we put detector here, for example detector or the molecule here. Okay, so it depend on that one. So the flux density as a function of the polar angle theta only, so we can calculate using this equation. Okay, and so the flux density component, if we have two sensitive area, okay, or between two angle, okay, so we can get the flux density as equal to this integration. Okay, and if the flux density or the detector depend on the theta and beta, okay, so the flux density per unit solid angle will be this in this equation, and the total flux density is using this equation. Okay, so we can get this we can calculate this total flux density. Okay, so these are one of the example. So from lecture number 1, we see that for treatment of disease, okay, so these are one of that. So brachytherapy for the breast cancer, I believe. Okay, so here these are the radiation. Okay, so the radiation will go past only one stream, okay, hitting the target and giving to the detector. Okay, so here we can see that this radiation does not moving or coming out like from our core mantle, kalau kita tengok dalam kita punya bumi, okey, ada pusat bumi tak keluar ke serata tempat, only kalau contohnya ini dia akan keluar hanya melalui Malaysia. Okey, tak keluar randomly dekat Antartika ataupun. So this radiation also we only in one direction. Okay, so we can get this visual distribution. Okay, so here is the one that we see the flux, this non-stuck fluence, flux density, energy fluence, energy flux density. So we can calculate this. Okay, when we do the experiment, we can calculate this, and we can decide the this flux density, the energy fluence, so that we can shorten the treatment, but at the same time we can kill the cancer. Okay, so that's all for this time. Thank you.